Hello everyone, I am Dr. Padmasree Lam, Professor in Department of ECE at VNR VJEC. So in previous video, we have learned about analysis of current series feedback amplifier. In today's class, we will learn about analysis of current shunt feedback amplifier. Topics covered in this video are derivation for current gain with feedback, derivation for input resistance with feedback, derivation for output resistance of current shunt feedback amplifier. This is the block diagram of current shunt feedback amplifier. In current shunt feedback amplifier, basic amplifier is current amplifier, and the type of sampler is used at the output terminals of the current amplifier is current sampler. Type of mixer is used at the input terminals of current amplifier is shunt mixer. So this is the connection for current sampler. This is the connection for shunt mixer. In the case of shunt mixer, source must be current source. So after identifying the type of the sampler, type of the mixer in current shunt feedback amplifier, you can observe what is the signal present at the input terminals of the feedback network. So in the case of current sampler, current flowing through the load terminals is I0. Same signal present at the input terminals of the feedback network, that is I0. In the case of shunt mixer, signal present at the output terminals of the feedback network must be current, that is related to feedback network. You can represent it with IF. So in the case of current sampler, input terminals of the feedback network is connected in series to output terminals of the basic amplifier. So the signal present at the input terminals of the feedback network must be I0. And in the case of shunt mixer, output terminals of the feedback network is connected in shunt to input terminals of the basic amplifier. Source must be current source. So therefore, output of the feedback network is IF. After identifying input and output signals of the feedback network, then you can easily find out gain of the feedback network or feedback factor is ratio of output of feedback network to that of input of feedback network. So beta is equals to IF by I0, where IF is output of feedback network and I0 is input of feedback network. Okay, so in current shunt feedback circuit, fraction of the output current is sampled and fed back in parallel with the input current through the feedback network. So therefore, feedback signal IF is proportional to I0. Feedback factor is IF by I0. So now you clearly understand this point. In current shunt feedback amplifier, basic amplifier is current amplifier, input of feedback network is I0 and output of feedback network is IF. So therefore feedback factor is IF by I0. So next we will see about derivation for current gain with feedback. The circuit represented in dotted lines is equivalent circuit of current amplifier. So gain of the current amplifier without feedback, you can represent it with AI. AI is equals to ratio of output current to input current, that is I0 to II. Okay, so AI is current gain without feedback. So in equivalent circuit of current amplifier, input terminals can be represented with Ri and output terminals of current amplifier can be represented with not an equivalent circuit. What is not an equivalent circuit? Current source in parallel with Norton resistance. So what is the magnitude of the current source? So from this expression, what did you get? I naught is equals to AI into II. Magnitude of the current source is AI into II is in parallel to R naught, where R naught is output resistance of the current shunt feedback amplifier without feedback, and Ri is input resistance of the basic amplifier without feedback. Okay. So see the direction of the current source, that is towards upwards. AI into II is magnitude of the current source, and R naught is output resistance of the basic amplifier without feedback, where Ri is input resistance of the basic amplifier. By observing this diagram, Is is current source and If is output of the feedback network. If is equals to beta I naught, and II is current flowing through the input terminals of the basic amplifier. These two are input terminals of the basic amplifier. These two are output terminals of the basic amplifier. Current flowing through the input terminals of the basic amplifier is II. Vi is voltage drop across Ri, and I naught is current flowing through the load resistance. Okay. Now we will see the derivation for current gain with feedback. So current gain with feedback is defined as ratio of output current of the feedback amplifier to that of input current of the feedback amplifier. So what is output current of the feedback amplifier? I naught. What is the input current of the feedback amplifier? Is. So therefore, current gain with feedback, AIF is I naught to Is. But current gain, now we have to derive the expression for AIF in terms of AI. What is AI? Current gain without feedback. Current gain with feedback, you can represent it with I naught. AI is equals to I naught by IA. So from this expression, you will get I naught is equals to AI into II. By observing the input loop, how many branches are there? There are 3 branches. Current is dividing in these all 3 branches. Apply KCL in the input loop. By applying KCL in the input loop, what did you get? Is is equals to II plus IF. Okay. So, but IF is beta I naught. Substitute IF in this expression. You will get II plus beta I naught. Okay. So from the expression of AI, you will get I naught is equals to AI into II. Substitute I naught in the expression of Is. Then you will get II plus beta AI into II. So you can take II as common here. So II into 1 plus beta AI. Okay. Substitute Is in the equation of 10. Then AIF is equals to I naught by II into 1 plus beta AI. So instead of I naught by II, what can you write? AI. So therefore AIF is equals to AI by 1 plus beta AI. So now you can clearly understand the terms present in this expression. AIF is current gain with feedback, AI is current gain without feedback, and beta is feedback factor. So from this expression, you can easily understand that current gain with feedback is less than that of without feedback by the factor of 1 plus beta AI. So next we will see the derivation for input resistance of current shunt feedback amplifier. So remember this point, basic amplifier is current amplifier. The circuit represented in these dotted lines is equivalent circuit of current amplifier. So now you have to derive the expression for RIF in terms of RI. What is RIF? Input resistance with feedback is RIF. What is RI? Input resistance without feedback, that is RI. So input resistance with feedback RIF is ratio of input voltage to input current of current shunt feedback amplifier. What is the input voltage? VI. What is the input current of current shunt feedback amplifier? IS. Therefore, RIF is VI by IS. Input resistance without feedback is Ri, that is equals to, what is the input current of the basic amplifier? II. What is the input voltage of the basic amplifier? Vi. So therefore Ri is equals to ratio of Vi to Ii. By applying KCL in the input loop, what did you get? Is is equals to Ii plus If. But IF is beta I naught. Therefore, by substituting IF here, IS is equals to II plus beta I naught. Okay. So, but I naught is equal, AI is equals to I naught by II. So, from this expression, what did you get? I naught is equals to AI into II. Substitute I naught as AI into II in the equation of IS. Then you will get II plus beta AI into IA. Okay. So this is the final expression for IS. Substitute IS in equation 11. So equation 11 is RIF is equals to VI by IS. By substituting IS in this expression of RIF, you will get VI by II into 1 plus beta AI. So instead of VI by II, you can write down RI. So therefore, RIF is RI by 1 plus beta AI. So this is the final expression for input resistance with feedback. So instead of this, you can write down RI. So what did you understand by seeing this expression of input resistance with feedback? RIF is less than Ri by the factor of 1 plus beta AI. So you can clearly understand the terms in this expression. RIF is input resistance with feedback and Ri is input resistance without feedback and AI is current gain without feedback, beta is feedback factor. Okay. So in current shunt feedback amplifier, input resistance decreases by the factor of 1 plus beta AI. So what is the reason for that? In input terminals of the basic amplifier, output terminals of the feedback network is connected in shunt to input terminals of the basic amplifier. Okay. So therefore, the shunt mixer is used at the input terminals of the basic amplifier. So why RIF is less than Ri? Output terminals of the feedback network is connected in shunt to input terminals of the basic amplifier. Therefore, input resistance decreases. Next, we will see output resistance with feedback, that is R0F. Derive the expression for output resistance with feedback in terms of R0. What is R0? Output resistance without feedback. Okay. So to derive the expression for R0F, set input source to 0. What is the input source? IS. IS is equals to 0. What is the meaning of current source? IS is equals to 0. Open circuit the input terminals. By open circuit the current source terminals. Open circuit current source terminals. By open circuit the current source terminals, input circuit has been modified like this. And disconnect the load resistance from the circuit and apply test voltage V between the output terminals and I is the test current. So V is the test voltage I is the test current. Output resistance without feedback R0F. R0F is ratio of test voltage to test current when Is is equals to 0. So you can find out Thevenin resistance also by using the same procedure, and where R0F dash is output resistance with feedback including load resistance. Okay. So now we have to derive the expression for R0F. So for that, what is feedback current? Feedback current IF is equals to beta I naught. What is the relation between I naught and I? I is flowing from right hand side to left hand side, and I naught is current flowing through the load resistance. So direction of I is opposite to that of I naught. So therefore I naught is equals to minus I. So IF becomes to minus beta into I. Okay. By applying KCL in the input loop, Is is equals to II plus IF. But to derive the expression for output resistance, set input source to 0. That means Is is equals to 0. Then II is equals to minus IF. Therefore, II is equals to beta I. Okay. Apply KCL in the output loop. By applying KCL in the output loop, this test current is dividing into these two branches. Okay. But AI into II direction, current source direction is opposite to this division current. Then you will get minus. So what is the expression for I? I is test current, that is equal to current flowing through this R0. How much current is flowing through this R0? Voltage drop across R0 is V, and current flowing through R0 is V by R0 minus AI into II. Why did you get minus? And direction of this current source is opposite to this direction. Then you will get minus. Okay. Now substitute II is equals to beta I in this expression. Then this expression becomes V by R0 minus beta AI into I. Okay. So take this beta AI into left hand side. Then you will get I into 1 plus beta AI into beta AI. You will get I into 1 plus beta AI is equals to V by R0. Okay. So same as like this. So output resistance with feedback R0F is equals to output resistance with feedback R0F is equals to V by I. By rearranging the terms, what did you get? V by I is equals to R0 into 1 plus beta AI. So therefore R0F, that means output resistance with feedback, is equals to R0 into 1 plus beta AI. So what did you understand by saying this expression of R0F? R0F is greater than R0. Greater than R0 by the factor of 1 plus beta AI. So now try to understand the terms in this expression. R0F is output resistance with feedback and R0 is output resistance without feedback. So R0F is greater than R0. So why output resistance increases in current shunt feedback amplifier? Because current sampler is used at the output terminals of the basic amplifier. So in current sampler, input terminals of the feedback network is connected in series to output terminals of the basic amplifier. So therefore output resistance increases than without feedback. So next we will see the conclusions of current shunt feedback amplifier. In current shunt feedback amplifier, feedback circuit is connected in shunt to the input terminals. Therefore, input resistance is decreases. Feedback circuit is connected in series to the output terminals. Therefore, output resistance increases. Current gain with feedback is AIF, that is equals to AI by 1 plus beta AI. Input resistance of current shunt feedback amplifier RIF is RI by 1 plus beta AI. So why the input resistance decreases in current shunt feedback amplifier? Output terminals of the feedback network is connected in parallel to the input terminals of the basic amplifier. Type of mixer is used in this amplifier is a shunt mixer. So that's why input resistance decreases. Coming to output resistance of current shunt feedback amplifier is R0F, that is equals to R0 into 1 plus beta AI. So output resistance increases. Why the output resistance of current shunt feedback amplifier increases? Input terminals of the feedback network is connected in series to output terminals of the basic amplifier. In the type of sampler is used in current shunt feedback amplifier is current sampler. Therefore, output resistance increases in current shunt feedback amplifier. So next we will see comparison of negative feedback amplifier. So these are the characteristics for comparison of all negative feedback amplifiers. Till now we have learned about different 4 types of negative feedback amplifier. What are those 4 types of negative feedback amplifier? Voltage series feedback amplifier, voltage shunt feedback amplifier, current series feedback amplifier, current shunt feedback amplifier. Now we will see various characteristics for all 4 feedback amplifiers. In voltage series feedback amplifier, what is the basic amplifier in voltage series feedback amplifier? Voltage amplifier. Voltage gain decreases, bandwidth increases, input resistance increases. Why input resistance increases? Series mixer is used in voltage series feedback amplifier. So output terminals of the feedback network is connected in series to input terminals of the basic amplifier. Therefore, input resistance increases. Output resistance decreases. Why output resistance decreases in voltage series feedback amplifier? Input terminals of the feedback network is connected in shunt to output terminals of the basic amplifier. Therefore, output resistance decreases. Harmonic distortion decreases. Noise also decreases. Coming to voltage shunt feedback amplifier. In voltage shunt feedback amplifier, basic amplifier is trans resistance amplifier. Trans resistance decreases. Bandwidth increases. Input resistance decreases. Why input resistance decreases in voltage shunt feedback amplifier? Shunt type of mixer is used in this amplifier is a shunt mixer. In shunt mixer, output terminals of the feedback network is connected in shunt to input terminals of the basic amplifier. Then input resistance decreases. Output resistance also decreases in voltage shunt feedback amplifier. In voltage shunt feedback amplifier, type of sampler is voltage sampler, and input terminals of the feedback network is connected in shunt to output terminals of the basic amplifier. Therefore, output resistance decreases. Harmonic distortion also decreases. Noise also decreases. Coming to current series feedback amplifier, type of basic amplifier is transconductance amplifier. Transconductance decreases, bandwidth increases, input resistance increases. What is the reason for that? Series mixer is used in current series feedback amplifier. Output terminals of the feedback network is connected in series to input terminals of the basic amplifier. So therefore, input resistance increases. Output resistance also increases in current series feedback amplifier because type of sampler is used in this amplifier is current sampler, and in current sampler, input terminals of the feedback network is connected in series to output terminals of the basic amplifier. Harmonic distortion also decreases, noise also decreases. Last type of feedback amplifier is current shunt feedback amplifier. In current shunt feedback amplifier, basic amplifier is current amplifier. Current gain also decreases with feedback. Current gain also decreases. Current gain also decreases with feedback. Bandwidth also increases. Input resistance decreases. What is the reason for this? Shunt mixer is used in current shunt feedback amplifier. In current shunt feedback amplifier, output terminals of the feedback network is connected in shunt to input terminals of the basic amplifier. Therefore, input resistance decreases. Output resistance increases. What is the reason for this? Type of sampler is used in this amplifier is current sampler. In current sampler, input terminals of the feedback network is connected in series to output terminals of the basic amplifier. Therefore, output resistance increases. Harmonic distortion decreases. Noise also decreases. By observing this comparison of all feedback amplifiers, see the characteristics. Bandwidth. Bandwidth increases in all 4 types of feedback amplifier, and harmonic distortion. Harmonic distortion decreases in all feedback amplifiers. Noise also decreases in all 4 types of feedback amplifiers, and remaining terms, input resistance and output resistance is varied, depends on type of the feedback amplifier. In voltage shunt feedback amplifier, input resistance and output resistance both decreases. In current series feedback amplifier, input resistance and output resistance both increases. In voltage series feedback amplifier, input resistance increases, output resistance decreases. In current shunt feedback amplifier, input resistance decreases and output resistance increases. These are the references for the preparation of the video. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.